Hey, what's up, guys? This is Chung here. So today, LeetCode number 718, maximum length of repeated subarray. Okay, so pretty straightforward. Given two integer arrays, nums1 and nums2, return the maximum common, right, subarray in both arrays. So for example, this one, the answer is 3 because the longest common subarray is 3 to 1, right? And then for this one, it's 5 because all 5 zeros they appeared in both arrays. And yeah, so that's it, right? So I mean the constraints 1000 and then range is 0 to 100, right? So for this one, for brute force, right? Obviously, the brute force will be we will find each of the subarray, right? From either from nums1 or from nums2, right? And then for each of the subarray, and then we check if that subarray exists in this nums2, right? But that would be too slow because to find all the subarrays in nums1 it will be a n square, right? And then to check existence in this nums2, I believe it's going to be another n square, right? So with this kind of constraints, it'll TLE. Okay. And so how can we solve it, right? I mean, so for this kind of double string or double arrays problem, DP is always an option, right? Basically, here basically we're defining like a DP, like a two state, right? I and J. Okay. So basically, this one means that from 0 to I in nums1, right? And from 0 to J in nums2. What are the longest, right? What are the longest common subarray? Basically, we just copy the description from the problem, right? And then so given that, right? Actually, no, this one is a little bit different because this one ending, right? Ending at I. Okay, this one is ending at J. Right, so the reason being is because we need to compare the nums1. We need to compare this I with J, right? If we need to check if they're the same, then we can. That's why then we can come up with this state transition function. That's why we need to add these constraints to our DP state definition, right? So basically, we check if this I and J are the same. If it is, then it's gonna be what? It's gonna be a 1 plus DP I minus 1 and J minus 1, right? So this is obvious, right? If the I is equal to J. But if the I does not equal to J, so for this one, we cannot do something like max DP I minus 1 J or DP I J minus 1. This is not right. And why is that? Because if it's not same, right? And the reason being is that we're trying to find the the subarray, not subsequence. If it's a subsequence, then this is right. But since we're getting a subarray, for the subarray, as long as the current one that does not match with each other, basically the DPIJ should be 0 instead of this one. Otherwise, it will carry over some incorrect number from the DPI minus 1 J and DPI J minus 1, because what I'm trying to say is that let's say we have DPI J minus 1 equals to 2, right? So which means that let's say from DP, basically from 0 to I and from 0 to J minus 1, we have two common. We have two the most common subarrays 2. But here, since I and J, they are not the same. But if we use this one, the DPIJ will still be 2, which is wrong, right? Instead of dpij should be 0 because I and j, they are not the same. So this is something we need to be careful here. Again, so because we're dealing with the subarray, not subsequence. Right? So that's the only thing for the DP, and then I guess we can start coding. And then after this one, we're gonna do another binary search plus rolling hash solution, okay, which is quite similar with the last week's weekly contest problem. Actually, it's a simpler version of that. Cool. So for DP, pretty straightforward, right? Very standard, two strings, two state DP. Excuse me. DP 0 n plus 1, right? For range n plus 1. Okay. For I in range of 1 to n plus 1, right? For j in range of 1 to n plus 1. Right, so pretty standard. We do this n plus 1 to make sure the I minus 1, j minus 1 will not go out of the boundary, right? We check if the nums 1, I minus 1, right? Since we are now the DP is 1 based, right? But the numbers is 0 based, right? J minus 1. If this is the case, then we can update the DP ij equals to max. Do we even need to do the max? Probably not. We can simply do this. DP I minus 1, J minus 1, right? This part, do I even need to do a max here? Let's see. Oh, and so the final result, you know, since the longest common could end up at any location, right? It doesn't have to be the end because the definition of DP is the ending with that. That's why, you know, we can maintain like an answer along the way. Basically, you know, every time when we have like a new DP, we can just update the answer, right? DP of I and j, and then we return the answer in the end. So that's it, I think. Okay, accept it. Yeah, so works, right? But it's pretty slow, as you guys can see, right? Huh? Actually, I'm kind of curious why it's that slow. Maybe because of the test case, because obviously this one is like n squared time complexity, right? We have n. This one is basically 10 to the power of 6. Shouldn't be that slow, but anyway, so basically that's the first DP solution, right? Pretty straightforward, right? Basically, we just simply compare. If the current one is the same, then we just update the current one with this one, right? Otherwise, we keep them at 0 because we're looking for the subarray, not the subsequence. Okay. Cool. So that's the first one. And for the second one is like it's a binary search plus rolling hash. And how does it work? Basically, for the binary search, right? If you guys saw my previous video, right, for the last week's weekly contest, this one is exactly not exactly the same, but it's a simpler version of that. You know, that one we have multiple arrays, but this one we only have 2. That's the only difference. Basically, we can binary search the answer, and why is that? Because, you know, if we have, let's say, if we have a k, if we know we have k size k, length k subarray in both arrays, then it means that there must exist another one, like k minus 1 size, right? And also k minus 2 until 0 or until 1, right? Because, for example, if we have 3 to 1, this 3, then it means definitely we can also find like a common subarray with length 2, right? Because obviously this is a 1. This one is also like 2, right? Similarly, we can also find one with 1, right? That's pretty obvious. That's why, if we binary search this answer, we can basically, this one, if we have like a helper function, can help us check if this two array exists like such size, right? And then once this value reach like certain value, basically, as you guys can see, so 1 is okay, 2 is okay, 3 is okay, but when it's reached 4, then 4 is not okay, right? That's how we can use a binary search to find the answer. And so after binary search, how can we find the common subarray in these two arrays, right? Like I said, we cannot use a naive like brute force solution to check the subarray one by one, right? There is like a rolling hash solution, right, which we can use to solve this problem. So basically, we simply loop through, given like a size k, right? We store all the rolling hash with a size k of the, with a size k subarray, right? And then we store it into a set from the nums1. We will do the same thing for nums2, and then we simply check if those two set have any intersect, have any intersection. If it is, then the helper function it will return true, otherwise false. Because in that way, we can simply get the rolling hash for the current subarray within O1 time complexity, right? So that's basically a technique to find all the subarray in array. Cool. All right, so let's start coding then. And for the rolling hash, right? I think I already talked about this several times. We simply just do this, right? So basically, we're gonna have like current cache. So for rolling hash, right? So let's say we have this one, you know what? If it's 10 base, right? So it's, for example, it's 2 1, right? So if this is the current hashing value, which is 312, and we're trying to get 4, right? So for this one, how do we get from 312 to 124, right? Basically, we do a 312 times 10, since it's 10 base, plus 4, right? And then we minus what? Minus 3000, right? So that's how we get this 124, right? And then this 3000 is basically 3 times 10 to the power of 3, which is the size of the subarray, right? So basically, this is how the rolling hash formula, right? Cool. And to do that, we need like two things. One is the base, and so for our case, the base is like 100, right? But we want to do a like 101 because for base, first it should be greater than the maximum number. Second, it should be a prime number. Okay, and the second one is going to be the mod, since we're doing a lot of multiplications. So that's why we also need to do a mod to prevent the overflow, right? Okay, cool. And then binary search, right? Okay, I'm gonna copy and paste these two parts, right? So the left boundary is obviously 0, and the right boundary is what? Is the minimum of the m of n, right? And then the binary search template, and so since we're getting the maximum, right? L plus middle, L minus L divided by 2, right? If the helper, right, is true, right? And it means, okay, this one could be the answer, and we're getting the minimum. So we're getting the maximum, right? The longest, which means that we're gonna have L equals to middle, right? And then else right equals to middle minus 1. Okay, so here every time we have a middle, we do a plus, L equals to middle, we do a plus 1 here. Okay, and then return either L or right. Okay, and then the helper function, right? Middle. We need 2 hash set basically, right? So, and then hash set 2. Since we'll need to do an intersect later on, okay? And then and then a base, right? 101, and then the mod. I just simply choose a like big enough number to make sure we'll avoid some a hash conflict, right? And then we have a current hash, right, equal to 0. So for the first array, right? For this one, we have current hash equals to current hash times base plus nums1 I, right? And then if the I is greater than the middle, right, that's when we need to subtract, right, some values from it. Nums1 dot I minus middle, right, because we're trying to remove the first one. It's going to be the times what? Times base of power of middle, right? But that's how this is basically this is the 3000. This is 3 and this is 1000, right? But here, the base times 1 to the power of middle, this one could be huge, and this calculation gonna be slow. That's why we're gonna pre-calculate this value. I'm gonna save it here, right? But even though to pre-calculate, so this thing could overflow basically, right? That's why we're gonna do a power of this one. That's why we're gonna use like power in Python function, right? So there's a base, there's like the middle, and then there's going to be a mod, right? So here we simply just times a here, right? And then we also gonna do a hash a mod on the hash itself, because this thing could also be big, right? That's why we're gonna do a mod here, and then if the I is greater than middle minus 1, right? If it reaches the the middle size, we add it to the hash set 1. Okay, current hash. Okay, so that's how we we calculate all the hash in nums1 with the size as middle, and we store it into a hash set 1. And then I'll just copy and paste here to do it with hash 2, right? It's going to be a 2, 2, and 2, right? And then in the end, we simply just check, right? We do a hash set 1 dot intersection of hash set 2, okay? And then we check, this one will return like another list. We check if the result is greater than 0. The length is greater than 0. If it is, then we know, okay, there exists it exists some subarray, right? And yeah, I think that's it. Okay, so if I run this one again, oops, one, weird. Base, middle, mod, current hash. Oh, here. Oh, I forgot to reset this value back to 0, right? All right. If I submit one more time, cool. Oh, as you guys can see, this one is much faster. And so why is that? Because let's check the time complexity, right? So here we have left and right. So this is like log n, right? and within the helper functions. So this one is n, right? This one is also n, and the intersect is also n, right? That's why this one is a log n instead of n square, right? That's why this one is faster than the previous one. Yeah, I think that's it. Yep. So I think that's it for this problem. I mean, the DP one is pretty standard, and the rolling hash one is I think it's also very useful. I recommend you guys understand it, right? Basically, we use the binary search plus rolling hash to check if there exists like such subarray with a certain length, right? Because the rolling hash can give us O1 time complexity when it comes to the hashing value for the new subarray. Right? Basically, it's going to be a sliding window, right? Plus rolling hash with some of the tricks here, because here, I remember in during last week's weekly contest, the test case was even stronger, basically. So basically, this mod will not be enough to avoid some hashing collisions. So I remember we had to increase this one to an even bigger number, or introduce a second hashing function, right, to solve that. But seems like this one, the test case is not that strong. That's why this two value works. Cool. Okay, I'll stop here then. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.